So welcome to Math 383, Complex Analysis. So what we're going to do today is we're going to continue our discussion of the complex logarithm. And so we're going to talk a little bit about what the logarithm is and give a good definition of it. And we're going to talk a little bit about spaces where it is defined. And if there's time at the end of class today, I'm going to talk about a fun problem I learned from my physics mentor at college, where it is all about where is this legal? This is a physicist being a physicist and just doing beautiful mathematics. And as you look at it, you go, can you justify any of this? Yes, if you look at the right space. So we really need to be aware whenever we're doing things, where are these operations legal? This is one reason why I hate the first part of the course, because we always have to be careful. So at what level have we proven, Cauchy's theorem and whatnot? What is the space where everything is defined? All right, so general items, we'll talk about the power of defining functions via integrals. So we have a lot of theorems that say if you can write something as an integral, then it's holomorphic. We have nice ways of tackling stuff like this. As always, we're going to try to generalize concepts from real analysis. The question will be, when are things similar to our intuition from real analysis, and when are they completely different? I could spend, I think, the entire class today just reviewing results we've already proven that are so different from anything we've seen in real analysis. And then we might get a little bit of a chance to see the power of accumulation. Okay. So because the last lecture was purely video, I wanted to just quickly state the open mapping theorem, maximum modulus principle, and the corollary. These I think on previous slides, but just for completeness, this way they're also in the slides from today. And again, this just shows the incredible power of Rouché's theorem. These are two remarkable consequences. The open mapping theorem that if f is holomorphic and non-constant, then the image of an open set is open. Very different than real analysis. The maximum modulus principle, that if you have a non-constant function, then it cannot attain its maximum in the interior. And since you're in open mapping, if you had a point in the interior that had the same value, absolute value as something on the boundary, which was the largest, well, if you take a small map, it would have to be a little bit larger locally. So that's a contradiction unless your function is constant. So again, completely different from real analysis in terms of the behavior. We've already seen before some examples of the power of the boundary. So where have we seen the theorem about the power of the boundary in complex analysis? Yes, if we do a contour integral, we can use that to define the function f of z by doing an integral of, say, f of zeta over zeta minus z along some kind of boundary curve. So just the value of the holomorphic function on a boundary is enough to determine the value everywhere. All right, so we need a couple of results, which hopefully you've talked a little bit about in real analysis. So the first is, a simply connected space. So there's lots of different types of, connected. So a donut is connected, but a donut is not simply connected. So if I give you a donut like this, let's try again. Big 3. Big 4. Awesome. Right, so if I give you something like a donut, and I talk to you about curves, I'll give you some curve like this. If I now try to give you another curve that has the same endpoints, let's say I draw the curve this way. So the curve is in the space, but I can't deform the curve. I can't deform the green all the way down to the red. And so this region is not simply connected. We cannot move, we cannot deform one path to the other. Yes. So basically, I mean, just move the green curve continuously until it becomes the red curve. So we talked about trying to write that as trying to write it as, say, t times the first curve, gamma 1 of z plus 1 minus t gamma 2 of z. And so if I write something like this, if I take t equals I guess I did it backwards, right? If I take t equals 0, I have the curve gamma 2. If I take t equals 1, I have the curve gamma 1. And this gives me a way to move from one curve to the other. And so it turns out that all the stuff that we're doing, what really matters is that we have a curve and we have the entire interior included. If the entire interior is included, do something like this without any trouble. The difficulty with something like the donut is we do not have the entire interior included. And that's what's causing. So that rebooted everything. Excellent. Always reboot. Okay. So the next thing to talk about is branch cuts. And so we've talked about the complex logarithm a little bit and about some of the issues. And the problem is, e to the 0 is the same as e to the 2 pi I n, where n is any integer in z. And so we have a problem if we go all the way around. So if I take the complex plane, and I go like this, here's theta equals 0, here's theta equals 2 pi. We have a problem if we come all the way around. This is like the old joke, doctor, it hurts me when I go like this. So what does the doctor say? Don't go like this, right? So the whole point of a branch cut is, well, if you have trouble if you go all the way around, what's the solution? Don't all go all the way around, right? This is from the Department of the Blatantly Obvious, right? So what we do is typically we take 0 and we throw away some curve going off to infinity. And we refuse to allow ourselves to cross that line. And so now, if I try to draw a path, and I want to come, I can't cross the line. I can do all strange things like that, but I've never gone a whole 360 degrees around. And so a branch cut is going to prevent me from having trouble like this. You could, of course, have other types of very interesting branch cuts where maybe you kind of spiral around and whatnot. We're not going to worry about that. For us, the most common branch cut is the principal case. So the principal branch cut. And in that case, we throw away this. Why do you think this is a good thing to throw away? Which log is not defined? The real log is not defined for negative. So this is a good choice. So good choice. The real log is not defined for negative numbers. So given that the real log is not defined for negative numbers, when we're extending it to complex numbers, why not just say that's going to be the line we're going to throw away? Clearly, throwing away 0 is a great idea. There's no angle that we can even assign to that. When you do your polar and spherical coordinates, polar and spherical are almost one-to-one, transformations from Cartesian to polar, Cartesian to spherical, except for the origin. For the origin, you can take any angle you want. So it's really good that we're not including the origin. So again, the book does a really good job of explaining all this stuff. I want to just try to concentrate on some of the intuition. So here's the big theorem. Suppose omega is a simply connected open set that contains 1, doesn't contain 0. So you should be thinking, complex plane without 0 in the negative reals. Then there's a branch of the logarithm defined by log sub omega of z, which has 3 properties. F is holomorphic, e to the f of z equals z, and f of r equals the log of r whenever r is a real number and near 1. So basically, we have a generalization of the standard logarithm. So in our mind, we should be thinking, here's, some set omega, here's 1, here is, oops, maybe, here is 0, and maybe there's our branch cut. So we have something like this. And we're saying in a region like this, we should be able to define a logarithm. If you want, just think very locally, very close to 1, there should be a definition of logarithm because we can't do too much harm if we don't move too far away. All right. And so we want to figure out how should we attack something like this. So the proof is to go back to a way of defining the logarithm. So we're going to look at the function f of z equals 1 over z. Why is this a good thing to look at? Well, in calculus, we have the logarithm, and we have its derivative is 1 over x. So the log of x is the integral from, say, 1 to x of 1 over t dt. So we can define the logarithm like this, or we could say the exponential of the logarithm equals x. Both definitions have advantages. Why do you think we are using the integral of 1 over t rather than the exponential of the logarithm? Yes. We like taking integrals, right? I hope you knew this when you were signing up for complex analysis, that this is going to be a class on integration. I have just found out that I am going to be teaching Math 140, Calc 2. This is going to be breaking one of my life goals, which was never to formally teach Calculus 2. I'd gone over 2 decades without ever having that happen to my schedule. So I will finally be teaching people how to actually integrate by integrating. I've never actually done that. So it's going to be an interesting experience. So we like integrating, or we like avoiding integrating, but we like to at least be avoiding integrating. So that's very different than looking at the exponential function. So looking at this function, big F of z is the integral over some curve gamma. And what is gamma? Gamma is a curve starting at 1 and ending at our point z. And because it's simply connected, it shouldn't matter what path we take. I actually don't like this notation. I like to put a little subscript z, so that when I look at the integral on the right, I can see that this integral depends on the point that I choose. It's in some sense, it's z understood, because I'm saying capital F of z equals this integral. Z's got to be somewhere. Where is z hiding? It's hiding in the gamma. And so the first thing is, it doesn't depend on path. So why doesn't it matter what path we take? What if we took another path? What would we know? Okay, so holomorphic integrals equal, why are the integrals equal? Good, because if we take the second path backwards, so if we rewind, there would be a closed curve. Closed curve, integral is 0 as holomorphic. So 2 integrals the same. So this is why it doesn't matter what path we take. And this is the power of looking at a path connected region. I can take any other path, they're all going to be contained in here. I can use Cauchy's theorem. Okay, so now that we have that, that tells us, that this integral is well defined. And you might remember the joy we had earlier in the semester where we were trying to define, and initially we only moved rectilinearly. We moved, east, west, and then we moved north, south. Then after a while, we said, actually, it doesn't really matter. We can move any path we want. But we had to be extremely careful in the beginning. Do we have to worry about the function 1 over z having a pole? I'm sorry? Why not? Yeah, omega doesn't have 0, so this is never going to be 0, so it's going to be a nice holomorphic function. Okay, and so we now have a holomorphic function. And so you can use the standard techniques. And you would get f prime of z is just going to be little f of z. And this follows the standard arguments. We have a nice curve. If you want, you could look at f of z plus h minus f of z over h. You could argue like that. You could use various results of holomorphicity. So now, if we want to look at the function point 2, e to the f of z equals z, we often study say g of z equals z e to the negative f of z. And what do you think we want to show about about this function g? Yeah, we want to show it's constant. In fact, more than just that, it's constant, it's equal to 1. We would get g prime of z is going to be 1 e to the negative f of z plus z e to the negative f of z, and then we would have f prime, which is just, made a mistake. There should be a negative sign, yes. Okay. So how does this help us? Yes. So little f of z is just 1 over z. So this is now the same as e to the negative f of z times 1 minus 1, which is just 0. I'm sorry? Because f of z is 1 over z. Right? And then we just note that g of 1 is equal to 1 as f of 1 equals 0. This is why it's nice to choose the point 1 to be in the region. Because if we're integrating from 1 to 1, you know, what is the integral from 1 to 1 of any nice function? Even if the function isn't nice, you know, unless the function is blowing up, you know, you're just integrating over a point, you're going to just get 0. So clearly, big F of 1 has to be 0. So big F of 1 just means your e to the f of 0 equals 1. Okay, good. So now we know the normalization constant. And then the last part is that f of r equals the log of r whenever r is a real number near 1. So that's the last part. So we now need now we need to just show that f of r equals the log of r whenever r is a real number and near 1. Well, here is my omega. Here's 1. Since omega is open, I've got at least part of the real axis near 1. And so if I just take z to be x, which is a real number near 1, then big F of z is actually big F of x, which is the integral from 1 to x of 1 over t dt. What does that equal? That's just the standard logarithm. So that's just going to be log of x. Yes? Well, for instance, -1 is, you know, we don't want it to be defined there. So it should basically be true anywhere where the real axis is in omega. It should be true in there. But we want to make sure we stay away from 0 in the negatives.
What if you have, say, like an open set that kind of like spirals around the origin of like two different places where different
So what you want is, I think, something strange like this, where this is going to be my branch cut.
Yeah.
Right? I believe in a situation like this, you will be okay.
So that just means that why you need 0, 1, because then you might have like pi I somewhere else.
Oops. So here's 1. I'm not sure if you would have a plus 2 pi I, because if we tried to take some kind of curve, you know, if I start here, I can't get back because I'd be crossing the branch cut.
Oh, no, I need to cross the real line.
If I cross the real line now over here, yes, because now if I do something like that, I've now gone, yes, good, excellent point. Then now I actually have gone around the whole amount. And this is why for all of these properties, you always want to talk about what's going on locally.
Why don't we, instead of trying that, why don't we just take the data,
Because you'll have a discontinuity if you start moving around. Well, we're never supposed to cross the branch cut. So points that are close to each other should have very similar behavior. So long as we can get to them within the open set. So we're never allowed to cross any of these boundaries. And that's the difference. So when we're walking along the circle, if there's no branch cut, I can start at 1, go all the way up to I, then -1, -I, and come back up to 1. And I've increased my value by 2 pi. And so now I'm associating 2 different values of theta to the same point, the point 1 plus 0i. And so we want to have something well defined. Eventually, we're going to talk about the square root of a number. So if I give you the square root of z, if I write z as r e to the I theta, the square root would just be r to the 1/2, and then e to the I theta over 2. And so we want to be able to handle quantities like this without too much trouble.
So when we do a branch that comes still take our data, we're not going to.
So here, as was remarked, we actually can have theta go beyond 2 pi as we keep walking.
That's not the value.
It's single value because we are never able to get to the same point. Because if we now try to come backwards, theta would be decreasing.
Well, can we just do a small circle right around this point? And theta, and you go back to the same point?
But if we start the small circle around here, it's going to be close to 0. And there would be a small positive, would be a small negative. We're not going to get to 2 pi. We're going to just do small changes and things will just be continuous in a small neighborhood. You've got to be able to make massive movements. This is similar to, if you've ever seen these questions about an ant walking and trying to figure out the geometry of the world that the ant lives on. If you have a sphere of radius 1,000 light years, you are not going to really notice that you have curvature. But if you start walking in a direction, you stay in that direction, you keep walking, you come back to where you started, then you know, okay, there must have been curvature. So if we do things small and locally, we're not going to see things. It's only if we can move all the way around and come back to where we started. And because of the branch cut, we never come back to where we started. It forces us to stay outside. All right. So the next part is talking about the shape of functions. And this is one of the big themes in mathematics. It's this idea of classification. If I tell you I have a set of objects with a given property, I could ask you, well, can you describe all the objects that have this property? What do they look like? What kind of form do they have? And the more you can say, the better. In modular forms, which is related to generalizations of the Riemann zeta function, it turns out they form vector spaces. And one of the most important modular forms lives in a vector space of dimension 1. So if you have a vector space of dimension 1, what can you tell me about all objects in that space? Not quite a point. The scalar multiples of a basis vector. So everything is a scalar multiple of something else. So boy, do you know a lot if you have a one-dimensional space. Unfortunately, we often have spaces that have many dimensions. If you remember your linear algebra, if you have a matrix that has n distinct eigenvalues, then you can diagonalize it. If you have a real symmetric or complex Hermitian matrix, it can always be diagonalized. But not every matrix can be diagonalized. Some matrices, the best you can do is put them in Jordan canonical form. How many people have seen Jordan canonical form? Okay, some. And so if you have Jordan canonical form, you have what's called generalized eigenvalues. And then the size of the Jordan block is the multiplicity of the eigenvalue. And so it's a classification theorem. The classification theorem we have here, this is building on our success earlier where we looked at the classification of meromorphic functions. And now we say we have a holomorphic function which is nowhere zero in a simply connected region omega, then we can write it as f of z is e to the g of z, where g is some nice holomorphic function. So can anybody give me a function that doesn't vanish on a region? So yeah, e to the z. So for example, your e to the z always works, as does e to the g of z. So in some sense, one direction is trivial. If I give you something of the form e to the g of z, clearly it's never going to be zero. It's the other direction that's interesting. So what if I give you, here's omega, and here, let's say it's a circle of radius 1 about the origin. And this is my omega. Can somebody give me a holomorphic function on omega that never vanishes? C. Right? Because z only vanishes at the center of the disk. Give me another function. Constant function. Z squared. Z to the n. Okay, what else? 1 over z. What else? So I'm staying away from this disk of radius 1 at the origin. 1 over z to the n, sure. What else can we do? We've still got, what, 32 minutes? 22 minutes. So if we can define the logarithm here, could the logarithm vanish? The other ones I was thinking of is, z minus a half, z plus 3/4. Right? I could do something like that, because the only zeros of that function. So these are all functions that don't vanish in a simply connected region omega. What must be true about all of these functions? If this theorem is true, yeah, we have to be able to write them as e to the g of z. Do these functions look like they have the form e to the g of z? No. So again, this is what I want to emphasize here. There should be some value added for coming to class. When I give you functions like this, I can write them as e to the g of z. Well, you might remember if I give you e to the x, I'm sorry. If I give you, say, x to the square root of 2, I can write that as e to the root 2 log x. And one of the ways you would calculate what's the derivative of x to the root 2, you can't use the binomial theorem to do x plus h to the root 2 minus x to the root 2 over h. You have to do it as e to the root 2 log x, and then use some results from calculus, such as the chain rule. So if I give you x to the root 2, I can solve it like this. More generally, if I give you z, maybe I can write z as e to the log of z. Well, wait a minute. I've got a simply connected region, and I've chosen it so it doesn't include, now, okay, it doesn't include 1, so it's not quite the previous theorem, but if I just adjust things a little bit, if I rescale things, I should be able to just adjust things so that 1 is in here, 0 is not. And I should hopefully be able to use the logarithm from last time to get something like this. So this is hopefully giving you a little bit of intuition on its way through.
So what if f is a non-bounded more function defined as 0? Non-bounded as 0.
Well, the theorem is just saying it can't vanish anywhere in the region.
Right, but you said you can't write a region along b of that function, right?
All right, say again what you have.
if I have a function that satisfies all the assumptions at
Mhm.
0,
At 0?
yeah, then you can't write it as the log of that function because log is not prime 0. So how would you write it?
Let me just take a page. So what function are you giving me?
I mean, I don't know a function that exists, but some function that defines that satisfies all those assumptions at 0.
So consider f of z equals z plus 1, and let's let omega equal the disk centered at 0 of radius 1/2. So this function is not 0 in that disk.
Right.
So we should be able to write it. So yes, so in omega, we do have f of z, which is z plus 1, can be written as e to the g of z for some g. So that's what we want. I mean, basically, it should be the log of z plus 1. So morally, the log of z plus 1 is the log of e to the g of z, which should just be g of z. So what we really want is we want to have a region where we can define a logarithm. So the earlier theorem gave us an example of where we can define logarithms. So this was a particularly nice logarithm, and it was chosen so that it would agree with the standard logarithm near 1. But we don't have to have it agree with the standard logarithm near 1. We just want a generalization of the logarithm. And essentially, if I have some kind of generalized logarithm, and here, what I should really do is I should write it log sub omega. The logarithm that's defined because of omega. You have more than one possible logarithm. Let's take a little digression. All right, log laws. What's someone's favorite log law? The log base b of. You gotta have favorite log laws. Yes. I'm sorry. All right, what else? Log base b of. Say it again.
Log base b of a.
All right, that's a special case of what we're going to get to later. So in the interest of time, the log of a sum is the sum of the logs. The log of a quotient is the difference of the logs. The log of a power is the power times the log. And then the real one is the change of basis. The log of x base b is the log of x base c over the log of b base c. And that's the most interesting of the log laws to prove. And what it tells you is that if you know logarithms in one base, you can essentially find logarithms in any base. Why do we care about this? Well, in the old days, people used to compute logarithms, and they used to construct tables of logarithms, as well as tables of sines, cosines, exponentials, digits of pi. Thankfully, or maybe unthankfully, these jobs are no longer, around. So you're going to have to find something else to do for your life. But it would be horrible if you would have to do this for every single base. The whole power of the change of basis is once you know logarithms in one base, whichever base is easiest, you can then get logarithms in any base. We're in some sense trying to do something a little bit similar here. We talked about how to construct a logarithm where we include 1, we don't include 0. Come on, it shouldn't really make that much of a difference. I should always be able to just map whatever set I have, map omega to omega tilde, where we've rescaled and translated things so that maybe 1 is in omega tilde and 0 is not. Now I have a logarithm on omega tilde, and then I rewind. if you want, this is similar to linear algebra. The principal axis theorem. If I give you an ellipse aligned with the coordinate axes, so that this is A and this is B, it's just x over A squared plus y over B squared equals 1. But what if the ellipse is poorly drawn and not aligned with the coordinate axes? Does anybody remember the formula if you're not aligned? Did anybody do this in linear algebra? All right, so here's U and here's V. Here's X and here's Y. Do we agree that it's easy to figure out what the equation of the ellipse is in the UV coordinate system? Because then it's aligned with the coordinate axis. So what you do is you start off with X, Y, you rotate to UV, then you write down, and then you rotate back. So you just use a rotation matrix to move the point X, Y into UV coordinates, write it down in UV coordinates, and then rotate back to being X, Y coordinates. And so you reduce the case of a general ellipse to just an ellipse aligned with the coordinate axis that you know. And so just dragging in it's x, y, 1 over a squared, 0, 0, 1 over b squared, x, y equals 1. This is the equation of an ellipse. So really, it's, I guess you want to do it, I can do it as, x, y transpose some matrix A, x, y equals 1. A is positive definite. How many people have seen positive definite? Every now and then, it's nice to be wearing a mask. Certain facial expressions cannot be seen. So you might have seen positive definite matrices if you were doing multivariable calculus and talking about, do I have a maximum or minimum? And you may need to go back to therapy and talk to a professional to get these memories back, because some of these memories are just locked down deep inside. But you had some of these formulas in multivariable calculus to tell when do you have a local minimum or a local maximum. And you have a local minimum if the upper left entry is positive and the determinant of the matrix is positive or something like that. Does this sound vaguely familiar? That you have all these different products, and depending on what, raise your hand if this sounds vaguely familiar. Something along these lines. And they gave you these terrible rules that almost came down from like Moses and Mount Sinai, that if these conditions happen, you have a minimum or maximum. Really what's going on is it's linear algebra. It's just rewriting what's going on locally in that region. If I give you a function f of x, y, I can write it as f of 0, 0 plus f sub x at 0, 0, x plus f sub y of 0, 0, y. And then I have the Hessian matrix, x, y. This is the matrix of second partial derivatives. Well, if I'm near a critical point, what's true about the gradient of f at a critical point? So this part here is just the gradient of f at 0, 0 dotted with the vector x, y. At a critical point, what's true about that? 0. So what this is telling you is near a critical point, my function, its Taylor series expansion is a constant, something that vanishes, and then I have some kind of quadratic form like this. Oh, this is kind of looking like a parabola. Wouldn't it be nice if that matrix, if the Hessian matrix were diagonal? Right? then it would be really easy to understand what's going on. So imagine this is diagonal. So imagine it's, say, xy, lambda 1, 0, 0, lambda 2, xy. In a situation like that, if both lambdas are positive, this is going to give you lambda 1 x squared plus lambda 2 y squared. So if both lambdas are positive, then this is always positive. So that means locally it's going to look like a parabola pointing upward in all the different directions. So you have a minimum. If both lambdas are negative, then locally it looks like a parabola pointing downward, and you're going to have a maximum. If one lambda is positive and one lambda is negative, then that means you're a local minimum in one direction, a local maximum in the other direction. This is a saddle point. This is multivariable calculus in a way that you can understand it, where these conditions come from. It all comes from linear algebra and just expanding the Taylor series about what's going on near the point of interest. And this is exactly what we were just doing with the ellipsis, is trying to write things down in a basis where things are nice. Well, my Hessian matrix may not be a diagonal matrix, but if my function is nice, the second derivative with respect to x then y is the same as the second derivative with respect to y then x. So H is a real symmetric matrix, which means it's diagonalizable, which means the change of basis theorem, the principal axis theorem, says I can change coordinates so that in this new coordinate system, the matrix is going to be diagonal, and that's where these conditions come from. So essentially, you have a local minimum if all the eigenvalues are positive. You have a local maximum if all the eigenvalues are negative. You have a saddle point if you have some of each. Okay, so this is a bit of a digression, but this is a good opportunity to fill in some potential gaps before you head off to graduate school. It's good to just see some of these things and see some of the connections between what you've been doing and what comes next. There are a lot of schools. I was fortunate to go to Yale, which had a class like this, where it was a unified year of linear algebra, multivariable calculus, point set topology, and vector analysis. And so we developed the language so that when we did multivariable calculus, we could actually talk about stuff like this. When you don't have linear algebra, it just makes no sense talking about how do we classify maximum and minimum of points. All right. So let me just continue, and if there are questions, I'll circle back. I want to at least say a few quick words about the proof. So, again, it's saying that we can write our function as e to the g of z for some holomorphic g. The idea is that there should be a logarithm. And since there should be a logarithm, that means there should be a way to define things. So fix some point z0, and we define a function as follows. So again, I'm going to put a little subscript z on what the book does, because I want it to be clear when I'm looking at this what's going on. Do I have to worry about the function f prime of w over f of w? Or do I have to worry about this being well defined? Why not? I'm sorry. Yeah, f doesn't vanish, so well defined as f of z does not equal 0 in omega. What is g of z not equal to? Yes. Yeah, it's just equal to our constant c naught. And so we choose so that f of z naught is equal to e to the c naught. And because f is not 0, there is a way to do that. If f was 0, we would have to worry about that, because we can't write 0 as the exponential. So everything is looking very good. Okay, and so now we have our function. And so now the question becomes, how do we show that this is well defined? What do you think this integral morally should be? Yes. Yeah, morally, it is the log of f of z, maybe up to a constant. Right. And again, if we just take the logarithm, what is the derivative of the log of f of z? It's 1 over f of z times f prime of z. And we know so if we look at what would g prime of z be? Yes. Yeah, just be f prime of z over f of z. So we can play, exactly the same types of games as before. And so, given that we have, 4 minutes left, I'm going to refer to the book, to finish the proof. I want to say a few words to prepare for what we're going to do next time. But it's the same type of argument as before. Morally, this argument looks like it's the log of f of z. If we take the derivative, we get 1 over f of z times f prime of z. And it's just making things rigorous and just being very careful about the regions that you're looking at. So you always have to then be able to appeal to some kind of growth properties of the function, that the function is nice, it doesn't have any zeros, this is going to be bounded, the curve is going to have a finite length. So if you just go through the standard arguments, you can then interchange the derivative and the integral. All right, so what I want to just quickly end with is just talking about quickly solving equations and roots to just prepare for the Weierstrass lecture that's coming up. So if I give you ax plus b equals 0, this is not that hard to solve. X is just negative b over a. If I give you ax squared plus bx plus c equals 0, there's a lot of ways to do this. Famous is the completing the square. We have an explicit formula for the roots. In general, however, we can't keep going. We can do cubic and quartic, but there is no closed form solution for the quintic and higher, depending just on roots and the coefficients of the polynomials. Now, there is a well-defined series of roots. Polynomial of degree n has n roots. That doesn't mean we can write them down. And just for the cubic, here are the 3 solutions for the cubic, ax cubed plus etc. Now, when you look at this, you could make things a little bit nicer. You could, of course, adjust things so that a equals 1, and then you could translate and you could make b equals 0. And if you do that, you would simplify things a little bit. But looking at this, it's quite clear why no one ever learned or memorized the cubic formula. This is just one of the solutions to the quartic. Again, you could play some of the games to make it a little bit better. What's particularly interesting for some of these roots is that you could have something where the roots are real and you have lots of i's and square roots. They all cancel at the end of the day to get you something that's real. And so what I want to end with is, let's say I want to prescribe some roots. Prescribe a function that vanishes at, say, z1, z2, z3. What function would vanish at z1, z2, z3? Yeah, so I could do z minus z1, z minus z2, z minus z3, and multiply by some constant. Another thing I could do is I could look at z minus z1, let's see, z minus z2, z minus z3, z minus z1, z minus z3, and then z minus z1, z minus z2. And the nice thing is, the first one vanishes at z1 and is non-zero at the other 2 points. So in fact, if I divide by z1 minus z2, z1 minus z3, what does this equal at z1? So what would the first piece equal at z1? It would equal 1. So I could just put in f of z1, and then similarly, f of z2, z2 minus z1, z2 minus z3, and then f of z3, z3 minus z1, z3 minus z2. And so now not only do I have a function that vanishes at prescribed points, it takes on the values I want to. And I can write it down very explicitly. So I can give you a function that vanishes at 3 points and takes on the 3 values. Can do for n equals 3. Who thinks I can do 4? 5. Dot, dot, dot. So long as n is what? Finite. And that's what we'll talk about next time is what do we do if it's no longer finite?